So today I wanted to do a bit of a deeper dive into a high-performance SQL engine. So just before you had the overview of Presto. So I wanted to do a talk which went into some depth about some specific problems that we're dealing with in Impala around resource management. So I wanted to motivate the problem, then we'll go a bit deeper into some of the techniques we've implemented and lessons we've learned. So the customers and the use cases and so on I'm talking about will be mostly motivated by Cloudera and our customers, but a lot of the work that I've been doing has been taking place in the open source Apache Impala project, in which I'm also a committer. So what is Impala? Impala is an open source SQL engine that's meant to enable analytics over large amounts of data. Typically, like an organization will have petabytes of data stored in a storage system like HDFS, S3, ADLS, Apache Kudu. And then Impala provides a way to do fast analytics over large amounts of data. So like in the Presto talk, it talked about wanting to do scans over large amounts of raw data, and Impala applies to a lot of similar use cases. We focus on low latency, so for some queries, providing sort of human scale response times of like under a couple of seconds so that people can sort of interact with the data on a human time scale. And we also support more complex analytics, so queries with larger numbers of operators and higher complexity. The query engine is distributed. We run across hundreds of nodes. And we're actually just a query engine. We're not a storage engine. So we focus purely on implementing this SQL over data stored in other systems. Our customers are mainly large enterprises. So one of the focuses for Impala is actually building enterprise-grade software that meets our customers' needs. So that includes features like security features like authorization, authentication, audit, and then other things like particularly resource management, which is what I'm going to talk about. And resource management is particularly relevant for our customers because of the way they use Impala. The Cloudera clusters are quite frequently used as a central data repository because we provide an affordable way to store large amounts of data, and we provide a lot of tools to ingest and do analytics over the data stored there. So a common pattern is that over time, you have a lot of valuable data in one place, and different groups from within a company discover that the data is valuable and useful to their needs. So it sort of attracts workloads from different groups, and those start off usually being exploratory and then graduate to being more production workloads, so like production applications or data pipelines. And pretty soon, you get into a situation where you're resource constrained. And that's because query processing over large amounts of data is inherently resource intensive. You use a lot of CPU doing all of the processing. A lot of operations are memory intensive just to pull data into memory, and then also to do operations like joins. We need to read and write a lot to disk. We use the network heavily because we're a distributed database and need to shuffle a lot of data. And then we can also sometimes produce a lot of load on other parts of the software stack. Operating system resources are actually often constrained, and external services, because we're not a monolithic database, we depend on other systems for metadata, and depending on the nature of the queries being run, they can induce a lot of load. So I kind of like to think of external services like the Hive Metastore as being a constrained resource. And so queries use a lot of resources, but they're also highly variable. Like you may have a mix of very small queries and very large queries as part of the same workload on the same cluster. So here, I was able to put together some data from our customer workloads, so just from a sample of our customers. And you can see this is the number of queries with a particular memory requirement. You can see that the vast majority are relatively small, so like not the vast majority, but a large number are relatively small, so like require under a gigabyte of memory. But then there's this long tail of queries that use 5, 10, 20 gigabytes per host, which is quite a lot of memory relative, if you consider that a single server probably has at most hundreds of gigabytes of RAM. And the heavy hitters, so the tail of large queries, are actually particularly interesting. A lot of times they're actually critical, so queries that absolutely must run no matter what. But sometimes they're also accidental. So one of the kind of dilemmas we face in doing resource management is that we need to be able to handle widely varying queries, and we also need to be able to handle them in very different ways depending on whether they're important or whether they're not important, like if they're accidental. Okay, so when you have a large number of queries running on a system and resources become scarce, then we tend to see a system go into a couple of different modes, and depending on the type of resource. So we have one category of resources are compressible, where as resources get scarce, performance degrades. That may or may not be a problem, depending on the requirements of the workload. But more problematically, you have incompressible resources, which, in the absence of a strategy to deal with the resource scarcity, things will start actually breaking. So like a classic thing is memory. If you start running out of memory, then queries might start failing in the absence of a strategy to actually deal with the problem. So I included, just as motivation, some of the error messages that Impala produces when it runs low on resources. Our customers, our users generally don't like seeing these. So one of the things we've invested a lot of effort into is to making query processing robust so that errors like memory limit exceeded are exposed to our users never or very rarely, because they just want to get their work done and get the results from their queries. Okay, what are we trying to do with resource management? I kind of look at it as sort of three priorities. One is to just stop stuff breaking, so keep the Impala service up and running queries. Keep individual queries from failing, because everyone likes it when they get their results back. And then once stuff is working reliably, then you sort of move on to other concerns like allocation of resources so that things run fast. Not everything can always run as fast as people would like, but you need to have policies to determine what fast enough means, so things like SLAs. Then also using resources efficiently is important. Like the more capacity you can get out of the same hardware, the better off you are. So these are the kind of the problems that we work on. And over time, we've sort of been kind of working our way down that list. So, as sort of a prioritization mechanism. Okay, so let's talk about specifics of how Impala works. So what does an Impala service look like? It's actually a collection of long-lived daemon processes. So you typically have one per host. And each of those processes can process many queries. So you might have two different queries, each of which is using resources on two different Impala daemons. We put a lot of work into doing in-memory query execution where possible to maximize performance. And the consequence of that is that Impala daemons exchange data directly through the network instead of materializing it, which means the query fragments from the query fragments of the same query need to be scheduled at the same time, so that the sender of the data can actually has a receiver to talk to. Then as a consequence of this design, with the long-lived daemons, we need to do resource management internally to the processes, which is something we've invested a lot of effort into. A bit of additional context, a Cloudera cluster usually has a range of services running on it, so like HDFS, Kudu, Yarn. So we have a top level of resource management using mechanisms like C groups, which allocates resources to services. Then the services within that, in many cases, do their own resource management, which is specific to the service. So Impala has like a concept of admission control pools. So the amount of resources allocated to a service can grow and shrink, both horizontally and vertically. So we have some things are supported now. There's some future work in this space. Impala was always designed to support dynamic membership changes to the cluster. So like unlike some traditional MPP databases, We're very good at growing at the moment. We have some in-progress work to make shrink more graceful so that we can drain queries from a node, particularly long-running queries, and then gracefully decommission that process. And yeah, we can, some resources you can grow and shrink the resource allocation dynamically. There's some future work around memory, again, because like shrinking the memory allocated does require, is a little bit more involved than increasing it. Okay, so let's go into the details of resource management. I wanted to talk about the high-level architecture and then share some insights around particular problems that we've solved. And I'm particularly going to focus on the memory management problem because it's where we've done some of the more sophisticated things. And it's also, I would say, the single most important resource in an analytic database because it's incompressible and because it's often limited. Okay, so as I mentioned earlier, Impala is a distributed system. So at some level, we need to manage resources within the whole cluster. So we have an admission control system, which is designed to allocate cluster resources to queries and then allocate determine which resources are in use or not. And that's where a lot of policies are implemented. So when a query comes into the system, we take the SQL text, the front end parses it, plans it, and produces a plan. And then once we know how we intend to execute the query, scheduling and admission control comes in, which is where we make resource management decisions. So with a new query, there are really three decisions that can make. It can run it immediately if resources are available. It can reject it immediately if a policy says to do that. So for example, if the query has some kind of anti-pattern that we don't want to allow in the cluster. Or you can queue it if we think that there may be resources available later for the query to run. So that admission controller looks at cluster-wide resources. Then once a query gets through admission control, we actually do all of our resource management locally within a single Impala daemon. And that was we've made some deliberate decisions in that area to do as much resource management within a single process as possible. So to limit the scope of the resource management decisions we have to make at the cluster level and make the single node and shift as much complexity as possible to the single node system, simply because writing correct single node code is actually easier than writing a correct distributed system. And so just to explain admission control further, it's actually decentralized. The original Impala architecture was intended to be totally decentralized. So every Impala daemon was in fact equal within the cluster. So any Impala daemon could accept incoming queries, plan them, schedule them, and admit them. And that has the benefit that it avoids a single instance becoming a bottleneck or a single point of failure. But as it turned out, that level of scale out for the coordination functionality generally isn't necessary. And it creates some complexity because you suddenly have hundreds of Impala daemons all executing the same resource management code in admission control. So we've moved to a more of an in-between model where we have on large clusters at least, we have a subset of the nodes handling this responsibility. So the good thing about this architecture is that it offers very low latency. We have no synchronous RPCs on the critical path of a query going through the planner and admission control, at least in the common case. The challenge there is that it means we need to share a lot of state. Particularly once a decision is made to admit a query, we need to propagate that information to all of the other admission controllers so that they can make decisions based on that. In order to avoid basically solving a distributed consensus problem, we made the state eventually consistent. So each coordinator makes an admission decision and then asynchronously propagates that decision to other coordinators. And the downside of that is that it is possible for resources to be overcommitted if, say, two queries arrive at the cluster at the same time and contend for the same resources. So there are some compromises in that architecture. Okay. Yeah. Okay, so to illustrate a bit more concretely, I wanted to talk about how we do memory-based admission control. So looking only at a single resource memory, how we make the decision about whether we have enough resources to run a query on the cluster. So it actually kind of looks like a bin packing problem. You can think of it that way. So each Impala daemon has some total capacity of memory, and each query has a memory limit which determines the maximum amount of memory it can consume. So pretty much the problem that we have to solve is packing queries into the available space in each Impala daemon without overfilling it. And we have some other policies there to sort of limit aggregate memory per resource pool. So, but yeah, the main thing is this kind of bin packing thing. And to illustrate what I said about the eventual consistency, so each Impala daemon knows its own internal state exactly because it knows what queries are running on it. But then it has to sort of asynchronously propagate that state through the state store, which is like our state dissemination mechanism. So for example, the purple query, query 4, that may have just started running recently on the Impala daemon, and the state may not be reflected on the coordinator. So that coordinator, if a new query came in at this point in time, it might actually overcommit memory on that Impala daemon. Okay, so that's potentially a problem, but we've tried to make our intra-node memory management mechanisms particularly robust, partially as a way to counteract the over-admission problem. We have some mitigations for over-admission, and we're sort of working on iteratively improving that as well. Okay, so, and kind of the high-level idea there is that if we make the intra-node mechanism more robust, then it actually makes the cluster-level policies easier to get right. And we spent a lot of time working on this problem, and it kind of boils down to being able to answer the question, if I run this query on this node now, is it actually going to succeed? Like, if I start it, especially if it's a large query and it might run for 30 minutes, do I know if it runs now, is it actually going to get to the end and return the results? Or is it going to run out of memory or something like that? And we've been able to solve that problem through cooperation of many of the subsystems in Impala. So the query planner, which has a view over the whole plan, that can actually compute the memory reservation, so the minimum amount of memory required to compute each plan fragment. We have a reservation mechanism, which for each node keeps track of what reservations have been claimed, so we avoid overcommitting memory. And that's just an accounting mechanism. Even if you have even if the accounting says that you have the memory for a query, you actually need to be able to fulfill that reservation. So we've implemented a buffer allocator that's designed to be very robust and only fail to allocate memory in very, very constrained circumstances, like if the operating system can't actually allocate the memory that we're entitled to. And then finally, just allocating the memory isn't sufficient. The algorithms in every query operator, so joins, aggregations, sorts, and so on, actually need to be able to, given a fixed amount of memory, execute reliably to completion. And once you put all of that together, you actually get a system which provides a high level of reliability and avoids out of memory in most scenarios. And to achieve this, we've deployed a range of techniques. And kind of the general theme, the way I like to think about it is that you're taking an incompressible resource memory and making it compressible. And usually that involves trading off execution speed for reduced memory consumption. And there are a bunch of techniques in this space. The database literature has covered this almost to death. But it's interesting. So you have things like spilling intermediate data to disk, so just paging it out to disk if you can't fit it all in memory. You can spill to network for some operators where it's safe to forward the data without processing it. You can scale down parallelism, you can scale down buffers. And there are a lot of tricks. So we've gotten to the point recently where the open source master supports resource constraints for most of the common query patterns that we see. So we sort of prioritized the operators based on how much memory they consumed and how frequently they used, and sort of gone down that list and tried to make them operate within a memory constraint. And this contrasts to maybe a year and a half ago where we had spill to disk and some of these other techniques, but it was still best effort to some degree. Like there was still a range of edge cases where these memory constraints didn't actually kick in. There are still edge cases, I'll be completely upfront, particularly because we're very flexible about the queries we let people run and the systems and the sort of third-party systems that we interact with. So we can have very large strings up to 2 gigabytes. User-defined functions can do all kinds of things, and we have to deal with data written by third-party tools. Okay, circling back to how the planner estimates memory. It's kind of interesting. I mentioned earlier that there's a memory reservation concept, which is just the absolute minimum memory. And this is actually a precise number based on the algorithms we've implemented, which is very useful for the reasons I mentioned earlier. Then another question is, how much memory do I need to run fast? This is actually a far more approximate question because you really need to execute the query to know how many rows are going to flow through the plan exactly. So we calculate that per node and then have an aggregation algorithm that works out which nodes run concurrently and then computes the global maximum. One question we had recently was how accurate the memory estimates are because they're inherently imprecise. We expect estimation error. So we were able to get our hands on a bunch of customer queries and plot the actual memory consumption versus our estimates. And this is a pretty messy plot. Like ideally, everything would be along the 45-degree line. But actually, this to us was actually pretty promising because, well, a lot of things are sort of not that far off the 45-degree line. And we also have a tendency to be conservative, to overestimate which are the points below the 45-degree line. So we're going to continue to iterate on these estimates based on the data we have. But this is already good enough to distinguish small queries, which use relatively little memory, versus large complex queries, which we may need to treat specially because either, as I mentioned earlier, they might be critical or they might be sort of rogue queries. So we have some more, so we're going to leverage that more in the future. Okay, so we've got a lot of work to do in this space. One thing we want to work on is improve our management of additional resources. So for example, CPU. We focused on memory first because of the reliability aspect, but CPU is also important because you want to admit enough queries to saturate your cluster, but not more to the point where everything slows down. We have a lot of opportunities to improve the policies we offer to make it easier for our customers to set up their clusters in a way that the workload is shaped and behaves in the way they want, so that different groups kind of get the share of resources that they're entitled to. And we can use the memory estimates there. Over emission is something we want to iterate on further. And then also, we want to make the out-of-the-box experience a bit better. Our goal there is that we want to get high availability without without any configuration. Currently, there's some manual configuration involved in like deciding how much memory to allocate to queries and so on. Yeah, okay, so this didn't quite fit into the previous part, but I wanted to leave a little bit of a side note as a counterbalance to all of the more complicated policies and mechanisms that I talked about earlier. Sometimes with the most success that we've had in resource management is not in adding new policies or complexity, it's actually just making things more efficient. And we had a couple of really big wins in that space this year. So we were able to dramatically reduce load on a lot of metadata services, particularly the HDFS name node, by adding file metadata caching. So that's been a big success. We see extremely high hit rates in a lot of production workloads. And we also did a big revamp of our RPC stack. So we moved from synchronous RPCs using Apache Thrift to an asynchronous model using the RPC stack from Apache Kudu. We saw like huge order of magnitude reductions in the number of threads in Impala processors and the traffic induced on external services by like Kerberos KDCs. Customers have started to deploy this into production, and we're seeing some like actually really nice speed up numbers on heavily utilized clusters. I think like 2x in some cases without any changes on their end. And yeah, just to illustrate how dramatic that RPC stack change was, this is the number of threads versus time. So we ran the workload first with the new RPC stack on the left, and it does not actually use many threads at all. Whereas on the right, you see the old stack, which creates a huge number of threads and potentially causes issues with the operating system in terms of hitting new limits or in general just degrading the performance of the operating system scheduler and causing kind of subpar performance. So yeah, this was a huge win. Okay, so what do I want you to take away from this talk? One thing is that analytic SQL with the high resource requirements and the big variation between queries actually benefits a lot from specialized resource management, which takes into account the knowledge of the workload and how query processing works internally. We hear a lot about containerization, and it's a very powerful tool, but it does not actually solve all resource management problems. Within the box, you kind of need to deploy some of the techniques that I talked about previously. Doing resource management in a distributed system, a lot of times the best way to solve the distributed systems problem is to push as much of the complexity down to the intra-node level because it's actually easier to reason about the behavior there and establish stronger invariants. So with things like the reservation management system, it's much easier to enforce invariants within a single node compared to invariants across a distributed system. Yeah, and finally, just sort of stepping back from the work we've been doing, we've come a long way in Apache Impala. So 2 to 3 years ago, we didn't really have this concept of executing within a resource constraint, and sort of incrementally shipping the components of that has made things dramatically more robust, but there's still a huge amount of work to do. And to get to the point where Impala is as robust as we want it to be and as easy to manage. Okay, so all this work was definitely not all my own. A bunch of people, present and former team members, contributed to this in some way, so I wanted to thank them. And I'll be available later on to answer any questions. Also, if you want any information about the Apache Impala project, we have a website, a mailing list, and all of those good things. So thank you.